In the summer of 1942, Ernest Lawrence stood before a blackboard covered in equations that would change the world forever. He wasn't designing a weapon. He wasn't building a bomb. He was solving an impossible puzzle: how to separate two nearly identical atoms that looked the same, weighed almost the same, and behaved almost identically. The answer he found would require something so audacious, so unprecedented that even today it sounds like fiction. The United States Treasury would melt down 14,700 tons of silver. Yes, actual silver reserves to build massive electromagnets that would purify uranium atom by atom. Welcome to World War II Scientists, where we uncover the incredible true stories of the brilliant minds who shaped history's greatest conflict. If you're fascinated by the hidden science behind World War II, hit that subscribe button and ring the notification bell because we're diving deep into classified projects, forbidden experiments, and the genius that won the war. This is the story of how metallurgists, physicists, and engineers turned precious metal into atomic fire, and how Japan never saw it coming until two cities vanished in blinding light. The Manhattan Project's electromagnetic separation program at Oak Ridge, Tennessee, represents one of the most extraordinary combinations of metallurgy, physics, and industrial engineering ever attempted. And it all started with a Berkeley physicist who refused to accept that atomic weapons were impossible. To understand why silver became essential to the atomic bomb, you first need to understand uranium's deadly secret. Natural uranium is a mixture of two isotopes: uranium-238, which makes up 99.3% of all uranium, and uranium-235, which comprises just 0.7%. These two isotopes are chemically identical. They react the same way, bond with the same elements, and form the same compounds. The only difference is 3 neutrons. Uranium-238 has 146 neutrons while uranium-235 has 143. Those 3 microscopic particles make all the difference between a radioactive paperweight and civilization-ending explosive power. Uranium-235 can sustain a chain reaction. When struck by a neutron, it splits apart and releases more neutrons, which split more atoms, releasing exponentially increasing energy in millionths of a second. Uranium-238 cannot do this. It absorbs neutrons and refuses to cooperate. For an atomic bomb to work, you need uranium that's at least 90% uranium-235. That means taking natural uranium and somehow removing 98% of the uranium-238, separating atoms that are 1.3% different in mass and chemically indistinguishable. In 1942, no one in the world had ever separated isotopes in quantities larger than micrograms. The Manhattan Project needed kilograms, eventually tens of thousands of kilograms. Every physicist who looked at the problem came to the same conclusion. It was theoretically possible but practically impossible. The industrial scale required was beyond anything ever attempted in human history. Ernest Orlando Lawrence was not a man who accepted impossible as an answer. Born in South Dakota in 1901, Lawrence had already revolutionized physics by inventing the cyclotron, a particle accelerator that used magnetic fields to spin particles in circles, accelerating them to tremendous speeds. By 1939, his 60-inch cyclotron at the University of California, Berkeley, was the most powerful atom smasher in the world, capable of producing particles with energies of 20 million electron volts. Lawrence understood magnetic fields better than almost anyone alive. He knew that charged particles moving through magnetic fields curve in paths determined by their mass. Heavier particles curve less sharply than lighter ones. In theory, you could ionize uranium atoms, give them an electric charge, accelerate them through a magnetic field, and watch them separate based on their tiny mass difference. The uranium-235 ions would curve in a slightly different arc than uranium-238 ions. With precise enough magnets and careful enough collection, you could separate the isotopes. Lawrence had done exactly this in his laboratory, separating isotopes of various elements, but he'd separated micrograms. The Manhattan Project needed tons of uranium processed to extract kilograms of pure uranium-235. To scale up his laboratory cyclotron to industrial proportions, Lawrence would need magnets thousands of times more powerful. And magnets require copper wire for their electromagnetic coils. Copper that in 1942 was desperately needed for shell casings, electrical wiring, and radio equipment. By late 1942, the United States was fighting a two-ocean war, building ships, planes, tanks, and weapons at unprecedented rates. Copper had become one of the most strategic materials in the war effort. Every artillery shell required copper for its rotating band. Every aircraft needed copper wiring. Every ship, every tank, every radio set demanded copper. The War Production Board had already allocated every pound of copper production for military purposes. When Colonel Kenneth Nichols, the district engineer for the Manhattan Project, approached the War Production Board requesting thousands of tons of copper for electromagnetic coils, he was flatly refused. There simply was no copper available. The project faced a crisis before it even began. You cannot build electromagnets without conductive coils. You cannot separate uranium isotopes without powerful electromagnets. You cannot build an atomic bomb without separated uranium-235. The entire Manhattan Project threatened to collapse over a material shortage. Lawrence and his team explored alternatives. Aluminum had been considered, but its conductivity was only 61% that of copper, meaning they would need even more of it, and aluminum was also desperately needed for aircraft construction. The problem seemed insurmountable. Then someone, accounts differ on exactly who first suggested it, proposed an audacious solution. The United States Treasury held enormous reserves of silver in vaults beneath the streets of New York City and other locations. Silver conducts electricity even better than copper, about 5% better. Silver wire wrapped around steel cores could create the powerful electromagnets Lawrence needed. It was unprecedented. It was radical. It was the only option they had. Colonel Kenneth Nichols was a West Point graduate and an engineer, but nothing in his training had prepared him for the meeting he was about to have. In early 1942, he walked into the office of the Under-Secretary of the Treasury to make one of the most unusual requests in American financial history. The conversation has become legendary in Manhattan Project lore. Colonel Nichols requested thousands of tons of silver from the Treasury reserves. The Undersecretary looked at him with apparent confusion and asked exactly how much silver Nichols thought he would need. Nichols, thinking in tons, as engineers do, replied that he would need approximately 6,000 tons. The Treasury official's response became famous. "Colonel, in the Treasury, we do not speak of tons of silver. We speak of troy ounces." The rebuke was gentle but pointed. Nichols was asking for precious metal reserves, not industrial materials. After Nichols recalculated and submitted his formal request in troy ounces, 395 million troy ounces to be precise, the Treasury Department faced an extraordinary decision. The silver he was requesting represented a significant fraction of the nation's entire monetary silver reserve. Under normal circumstances, such a request would be unthinkable, but these were not normal circumstances. The Manhattan Project operated under the highest possible classification priority. Whatever was needed would be provided. After consultation with Secretary of the Treasury Henry Morgenthau Jr. and ultimately President Franklin Roosevelt, the Treasury agreed the silver would be loaned, not given, to the Manhattan Project with the strict understanding that every ounce would be accounted for and eventually returned. Between 1942 and 1943, one of the most unusual material movements in American history took place in complete secrecy. From the United States Bullion Depository at West Point, New York, convoys of armored trucks began transporting silver to industrial facilities. The silver came in various forms: bars, coins that had been melted down, and industrial silver from Treasury reserves. In total, 14,700 tons of silver, worth approximately $400 million at 1942 prices, or roughly $8 billion in today's money, was transferred to the Manhattan Project. The silver was transported to facilities where it would be processed into wire. The metal had to be refined to specific purity standards, then drawn into wire of precise diameter. The tolerances were exacting. The electromagnetic coils had to be wound with precise spacing and consistency to generate uniform magnetic fields. Any impurity in the silver could create resistance irregularities that would distort the magnetic field and ruin the isotope separation. Security was extraordinary. The trucks traveled with armed guards. The silver's destination, a mysterious project in Tennessee, was not disclosed even to most of the guards. Only a handful of people knew what the silver would be used for. Treasury accountants tracked every ounce with obsessive precision. The silver was on loan, and the government expected every ounce to be returned when the war ended. The pressure on the Manhattan Project's materials division was immense. Lose even a fraction of this precious metal and there would be hell to pay. While silver was being transported, an entirely new city was being constructed in the Tennessee hills. Oak Ridge, Tennessee did not exist on any map. The site selected for its remoteness, access to TVA electrical power, and availability of water for cooling would become one of the largest construction projects in world history. At its peak, Oak Ridge employed 75,000 workers who had no idea what they were building. The electromagnetic separation facility given the code name Y12 would house the Calutrons, California University's cyclotrons that Lawrence had designed. The scale was staggering. Each Calutron consisted of a massive magnet shaped like a racetrack oval, 122 feet long, 77 feet wide, and 15 foot tall. Inside vacuum chambers within these magnets, uranium ions would be accelerated and separated. The magnets required those thousands of tons of silver wire wound around steel cores to generate magnetic fields of extraordinary power. The construction presented nightmarish logistical challenges. Each magnet weighed hundreds of tons. The buildings to house them had to be constructed with foundations capable of bearing enormous weight. The vacuum systems had to be perfect. Any air leak would cause uranium ions to collide with air molecules and scatter. Electrical systems had to provide enormous amounts of power without fluctuation. Cooling systems had to prevent the magnets from overheating. And everything had to be built by workers who couldn't be told what they were building. Oak Ridge operated under strict compartmentalization. Workers knew only their specific task, nothing about the larger purpose. The Calutron was a technological marvel that pushed 1940s engineering to its absolute limits. The name itself, a contraction of California University cyclotron, honored Lawrence's Berkeley laboratory, where the concept was developed. Each Calutron unit consisted of several key components working in precise coordination. At the heart was the source where uranium tetrachloride was vaporized and ionized, giving uranium atoms an electrical charge. These ions were then accelerated through an electric field to high velocity. As the speeding ions entered the magnetic field created by the silver wound electromagnets, they began to curve. The uranium-238 ions being slightly heavier curved in a wider arc, while the lighter uranium-235 ions curved more tightly. After traveling through a 180 degrees arc, the two isotope streams would be separated by about 2 centimeters, less than an inch. At the end of their curved paths, collection pockets would catch the separated isotopes. It sounds simple in principle, but the execution was extraordinarily complex. The magnetic field had to be absolutely uniform. Any variation would blur the separation. The vacuum had to be near perfect, pressure of less than 1/millionth of atmospheric pressure. The ion source had to produce a steady consistent beam. The collectors had to be positioned with millimeter precision. Temperature had to be controlled. Thermal expansion would throw off alignments, and the entire system had to run continuously for weeks to accumulate useful quantities of uranium-235. Each Calutron represented the coordination of dozens of systems, each operating at the edge of 1940s technological capability. The electromagnets themselves were engineering marvels. Each racetrack-shaped magnet required miles of silver wire wound around iron cores. The silver had been cast into billets drawn into wire of specific diameter, and carefully insulated. The winding process was painstaking. Each coil had to be wound with precise tension and spacing. Too loose and the magnetic field would be weak and irregular. Too tight and the wire might break under thermal stress when electrical current heated it during operation. The completed magnet coils were enormous. Some weighed over 400 tons. They were so large that special railroad cars had to be constructed to transport them to Oak Ridge. Once installed in the Y-12 building, they were connected to massive electrical systems. When energized, they drew enormous amounts of electrical power. The Oak Ridge facility consumed more electricity than most American cities. The Tennessee Valley Authority had built dams specifically to provide power for Oak Ridge. The magnetic fields generated by these silver coils were extraordinarily powerful, strong enough to pull tools from workers' hands, magnetize wristwatches from across the room, and make compasses useless within hundreds of feet. Workers had to be careful not to carry any ferromagnetic materials near operating magnets. There were reports of wrenches and other tools flying through the air and slamming into magnet housings. The power of these fields was both impressive and dangerous. Yet, this power was exactly what was needed to bend the paths of uranium ions with sufficient precision to separate isotopes differing by only 1.3% in mass. One of the Manhattan Project's best-kept secrets was that much of the actual Calutron operation was performed by young women, many of them recent high school graduates from rural Tennessee. The project recruited them specifically because they could follow complex procedures precisely without needing to understand the underlying physics. These women, later called the Calutron girls, were trained to monitor instruments, adjust controls, and maintain the delicate balance required to keep the Calutrons operating at peak efficiency. They watched dials and gauges, made minute adjustments to electrical current and magnetic field strength, and recorded data with meticulous care. They worked in shifts around the clock, keeping the uranium separation running continuously. What made their role remarkable was that they weren't told what they were doing. They knew they were adjusting electromagnetic equipment to separate materials, but they didn't know those materials were uranium isotopes. They didn't know they were contributing to an atomic bomb. Many didn't learn the truth until after Hiroshima, when the Manhattan Project was finally revealed to the public. Yet, their work was absolutely critical. The Calutrons required constant attention and adjustment. Automated controls of the era weren't sophisticated enough to maintain the precise conditions needed. Human operators following procedures developed by physicists and metallurgists could achieve separation efficiencies that automated systems could not match. Some of these women became extraordinarily skilled, developing an intuitive feel for the equipment that even veteran physicists admired. They could diagnose problems by the sound of the equipment or subtle changes in instrument readings. Their contribution to the Manhattan Project was incalculable. Although the Calutrons themselves were technological marvels, the metallurgical challenges of building and operating them were equally formidable. The uranium feedstock, uranium tetrachloride, was extraordinarily corrosive. It attacked most metals, especially at the high temperatures required for vaporization. The source chambers where uranium was vaporized had to be constructed from special alloys that could withstand both the corrosive chemistry and the high temperatures. Graphite components were used extensively because graphite could withstand heat and was relatively resistant to uranium compounds. The collection pockets where uranium-235 accumulated faced their own challenges. As uranium-235 accumulated, it would form deposits on the collector surfaces. These had to be carefully removed without contamination or loss. Every fraction of a gram of uranium-235 was precious. It took enormous effort to produce, and every milligram lost was a setback. The vacuum chambers themselves required special attention. They had to maintain near-perfect vacuum while withstanding the stress of enormous magnetic fields outside and the presence of corrosive uranium compounds inside. Joints had to be perfect. Any leak would ruin the separation process. Gaskets and seals had to be made from materials that wouldn't degrade under the operating conditions. The silver wire and the electromagnets faced thermal stress. When electrical current flowed through the coils, resistance heating raised temperatures. The silver had to be cooled to prevent damage. Cooling systems using water or oil were integrated into the magnet structures. The metallurgists working on the Manhattan Project had to solve problems that had never been encountered before, often with little time for testing or experimentation. When the first Calutrons at Oak Ridge became operational in late 1943, optimism ran high. Finally, after years of theoretical work and months of construction, uranium-235 would begin flowing. Reality proved far more difficult. The initial operations were plagued with failures. Vacuum chambers leaked. Ion sources failed. Magnetic fields weren't uniform. Electrical systems overloaded. Most devastatingly, some of the enormous magnets themselves failed. In one case, the sheer force of the magnetic field during startup caused structural damage. Components that weren't adequately braced were pulled out of alignment by magnetic attraction. In another incident, electrical insulation failed, causing arcing that damaged expensive equipment. The uranium feed systems proved problematic. Uranium tetrachloride was difficult to handle and tended to clog delivery systems. The high temperatures required for vaporization caused thermal stress that led to mechanical failures. Collection efficiency was far below theoretical predictions. Much of the uranium was depositing on chamber walls instead of in the collectors, requiring difficult and dangerous cleaning operations to recover it. Ernest Lawrence, whose design formed the basis of the Calutron, traveled repeatedly to Oak Ridge to troubleshoot problems. The pressure was immense. The Manhattan Project was racing against fears that Germany might develop an atomic bomb first, and every delay was potentially catastrophic. The Calutron operators, both the young women monitoring controls and the engineers supervising them, worked grueling hours to identify and solve problems. Gradually, through exhaustive trial and error, improvements were implemented. Vacuum systems were redesigned, magnet supports were reinforced, feed systems were modified, collection procedures were refined. By mid-1944, the Oak Ridge Calutrons were finally operating with reasonable reliability, though efficiency remained frustratingly low. Each Calutron was producing only grams of uranium-235 per day, and the Manhattan Project needed kilograms. The solution was to build more Calutrons and to implement a two-stage separation process. The first stage, called alpha Calutrons, would perform rough separation, enriching natural uranium from 0.7% uranium-235 to about 10 to 20% uranium-235. This partially enriched uranium would then be fed into beta Calutrons, which would perform fine separation, enriching the uranium to weapons-grade purity above 90% uranium-235. This two-stage process dramatically improved overall efficiency. The alpha stage could process uranium quickly without requiring extreme precision. The beta stage, working with pre-enriched feed, could achieve high purity more easily. Eventually, 1,152 Calutrons were installed at Oak Ridge in multiple buildings. Alpha and beta racetracks arranged in massive halls. The scale was unprecedented. The electromagnetic separation buildings at Y12 formed one of the largest industrial facilities in the world. The electrical power consumption was staggering. The silver requirements exceeded even initial estimates. Additional silver had to be borrowed from the Treasury to complete all the planned Calutrons. Workers became increasingly skilled at operating and maintaining the equipment. Procedures were refined through experience. Slowly, painfully, the production rate of uranium-235 increased. By late 1944, Oak Ridge was producing weapons-grade uranium-235 at a rate that made an atomic bomb feasible. The metallurgists and physicists had succeeded in solving what many had thought was an impossible problem. While electromagnetic separation using silver magnets was proceeding at Oak Ridge, the Manhattan Project was simultaneously pursuing other uranium enrichment methods. The project's leadership, understanding that no single approach was guaranteed to work, had decided to pursue multiple paths in parallel. Gaseous diffusion being developed at another Oak Ridge facility called K25 used the principle that lighter uranium-235 hexafluoride molecules would diffuse through porous barriers slightly faster than heavier uranium-238 hexafluoride molecules. Thousands of stages of diffusion could theoretically produce enriched uranium. However, the gaseous diffusion plant required enormous facilities and faced its own daunting technical challenges. Developing barrier materials with holes of exactly the right size was extraordinarily difficult. Thermal diffusion, which used temperature gradients to separate isotopes in liquid uranium hexafluoride, was also being explored. Centrifugal separation using the principle that heavier isotopes would migrate outward in a spinning centrifuge was investigated but ultimately not pursued at production scale during the war. Each method had advantages and disadvantages. Electromagnetic separation using Calutrons was slow but could produce very high-purity uranium in a single pass. Gaseous diffusion was faster but required many stages and enormous facilities. The Manhattan Project strategy was to let the methods compete and complement each other. Eventually, partially enriched uranium from the gaseous diffusion plant was fed into Calutrons for final enrichment, combining the speed of diffusion with the precision of electromagnetic separation. This hybrid approach proved highly effective. The accounting of the electromagnetic separation program reveals staggering numbers. The 14,700 tons of silver borrowed from the Treasury represented one of the largest material loans in history. At the time, it was worth approximately $400 million, roughly $8 billion in 2025. But the silver was only a fraction of the total cost. The Y-12 electromagnetic separation plant cost approximately $477 million to construct and operate, about $9.5 billion in today's money. The entire Oak Ridge facility, including gaseous diffusion and other operations, cost over $1.1 billion in 1940s dollars, roughly $22 billion today. The electrical power consumption was almost beyond comprehension. The Oak Ridge facilities consumed enormous amounts of electricity. At peak operation, the Calutrons alone drew more power than many American cities. The Tennessee Valley Authority had constructed dams specifically to provide electricity for Oak Ridge, representing additional infrastructure costs. The human cost was also significant, though measured differently. 75,000 people worked at Oak Ridge during the war, most having no idea what they were building. They lived in hastily constructed housing, worked long hours under demanding conditions, and maintained absolute secrecy about their work. The security measures were oppressive. Mail was censored. Phone calls were monitored. Movements were restricted. Workers were fired for asking too many questions. The strain on relationships, health, and mental well-being was considerable. Yet they persisted, driven by patriotism and the knowledge that their work, whatever it was vital to winning the war. By July 1945, the Oak Ridge Calutrons had produced approximately 64 kilograms of uranium enriched to about 80% uranium-235 with about 50 kilograms enriched to 89% or higher. This was enough for one atomic bomb. The uranium was shipped to Los Alamos, New Mexico, where Robert Oppenheimer's team was designing and assembling the weapons. The uranium would be used in the Little Boy bomb, destined for Hiroshima. Little Boy used a gun-type design. One piece of uranium-235 would be fired into another piece, creating a supercritical mass that would produce a nuclear explosion. The design was considered so reliable that it was never tested before being used in combat. All the electromagnetic separation, all the silver magnets, all the work of thousands of people had produced enough uranium-235 for a single weapon. The metallurgists and physicists who had purified this uranium knew its purpose by now. The Manhattan Project's goals were no longer secret to those with high-level clearances. Some struggled with the moral implications. They had solved an unprecedented material science and physics challenge, but the result would be a weapon of unprecedented destructive power. Others believed it was necessary to end the war and save lives that would be lost in an invasion of Japan. On July 16, 1945, the Trinity test in New Mexico proved that atomic weapons worked. That test used plutonium from reactors, not uranium from Oak Ridge. But the success of Trinity confirmed that atomic weapons were viable, and that the uranium bomb, simpler in design, would certainly work. The uranium Little Boy had been years in creation. It would be used only once. At 8:15 a.m. local time on August 6, 1945, the B-29 bomber Enola Gay released the Little Boy bomb over Hiroshima, Japan. 43 seconds later, at an altitude of 1,968 feet, the uranium-235 that had been separated atom by atom in the silver wound magnets of Oak Ridge achieved critical mass. In a fraction of a second, uranium atoms split in an exponential chain reaction, converting matter directly into energy. According to Einstein's equation, $E=mc²2, the explosion released energy equivalent to approximately 15,000 tons of TNT. The temperature at the hypocenter reached several million degrees. A blinding flash visible from miles preceded a shock wave that flattened buildings across a 2-mile radius. A massive mushroom cloud rose over 30,000 feet into the atmosphere. Between 70,000 and 80,000 people died instantly. By the end of 1945, the death toll had reached approximately 140,000 from direct effects and radiation exposure. Hiroshima, a city of 350,000, was essentially destroyed. In Tennessee, most Oak Ridge workers still didn't know what they had been building. Then the news broke. President Truman announced that an atomic bomb, a weapon deriving its power from the basic forces of the universe, had been dropped on Japan. He specifically mentioned Oak Ridge, Tennessee, as one of the facilities that had made the bomb possible. Suddenly the mysterious work, the secret equipment, the careful separations they had been performing, it all made horrifying sense. The young women who had operated the Calutron controls, a few units were maintained for isotope separation now understood that they had been enriching uranium for an atomic bomb. The vast majority was dismantled. The metallurgists who had designed systems to handle uranium for other purposes now understood what they had been component production during the Cold War. Reactions varied from pride to horror. Oak Ridge transitioned from a secret city to a real city. The Manhattan Project faced an unusual task, nuclear research returning 14,700 the electromagnetic separation of uranium isotopes continued to be used occasionally for special purposes. But every ounce would be accounted for at the industrial scale of World War II. Beginning in 1945 more efficient methods through the late 1960s, gaseous diffusion, the silver was gradually recovered from the electromagnetic separation for uranium enrichment. The magnets were carefully dismantled, had served their purpose, the wire was removed and the silver was melted down. The electromagnetic separation program for all its ultimate supersession by other technologies represented a remarkable achievement in metallurgy. The final tally showed that a small amount of silver had been lost during processing. The engineers who designed and built the Calutrons solved problems that had never been solved before at unprecedented scale and speed. This was within acceptable tolerances given the industrial magnetic fields could separate isotopes was vindicated despite enormous technical challenges. The Treasury considered the loss of developed materials that could withstand the corrosive uranium compounds. Most of the silver was successfully conditions and went back into Treasury science significantly. Some of the Calutron equipment was preserved. A few units were maintained for isotope separation for research purposes. The vast majority was dismantled. The Y-12 facility continued operating for other purposes, including weapons component production during the Cold War. Oak Ridge transitioned from a secret city to a real city, though one still dominated by nuclear research and production. The electromagnetic separation of uranium isotopes continued to be used occasionally for special purposes, but it was never again used at the industrial scale of World War II. More efficient methods, improved gaseous diffusion, and eventually centrifuge technology superseded the Calutron for uranium enrichment. The silver magnets had served their purpose and passed into history. The electromagnetic separation program for all its ultimate supersession by other technologies represented a remarkable achievement in metallurgy, physics, and industrial engineering. The scientists and engineers who designed and built the Calutrons solved problems that had never been solved before at unprecedented scale and speed. Ernest Lawrence's basic insight that magnetic fields could separate isotopes was vindicated despite enormous technical challenges. The metallurgists who developed materials that could withstand the corrosive uranium compounds and extreme operating conditions advanced materials science significantly. The use of silver as a substitute for copper demonstrated creative problem-solving under resource constraints. The industrial scaling of a laboratory technique to production levels required innovations in manufacturing, quality control, and systems engineering that influenced post-war industry. The operational experience gained at Oak Ridge, managing complex technical systems with multiple interdependent variables, training operators to handle equipment they didn't fully understand, maintaining quality under pressure, provided lessons that applied to many subsequent technical endeavors. The Manhattan Project's approach of pursuing multiple solution paths simultaneously rather than betting everything on a single method became a model for managing technical risk in large projects. Perhaps most significantly, the electromagnetic separation program demonstrated that impossible problems could be solved when sufficient resources, talent, and urgency were brought to bear. The fact that the United States was able to borrow from the Treasury and transform a precious metal into a wartime industrial necessity highlighted the extraordinary centralization of power and resources during the war. The final accounting of the project reveals the true cost of success. The silver loan was only a fraction of the expenditure. The cost to build and operate the Y-12 plant and its supporting infrastructure represented billions of today's dollars, a testament to the fact that the Manhattan Project was not a small scientific effort, but a massive industrial undertaking. The sheer volume of electricity consumed at Oak Ridge underscores the massive scale of the effort, surpassing the power needs of entire American cities at the time. The story of the Calutron girls remains one of the most compelling human elements. Their intuitive skill, their ability to perform complex, precise tasks without knowing the terrifying implications of their work, allowed the process to succeed where automated systems failed. Their quiet contribution to the largest scientific gamble in history is a hidden story of WW2 that deserves to be remembered. The eventual use of the uranium purified by the silver magnets confirmed the terrifying success of the effort. The destruction of Hiroshima, while a military and political decision, was made possible by the quiet, meticulous work done in the secretive Tennessee hills. The story of the silver that helped build the bomb is a perfect encapsulation of how far ingenuity, resourcefulness, and a willingness to take unprecedented risks can push technological boundaries during a time of total war. The legacy of the electromagnetic separation program extends beyond its eventual obsolescence. It laid foundational knowledge in isotope separation, large-scale vacuum technology, and high-power electromagnetism that fueled subsequent scientific and industrial developments in the post-war era. The ultimate moral weight of the project fell on the shoulders of the scientists and leaders. They successfully solved an impossible puzzle, using a daring, unprecedented solution, turning $8 billion in silver into the coils of a terrifying magnetic separation machine. The little boy bomb, a product of their relentless effort, achieved its goal, ending the war. The silver was returned. The terror of the atomic age began. The story of the silver magnets remains the most audacious footnote in the history of the Manhattan Project.